When engineers design aerospace-grade titanium components, they face a high-stakes challenge, predicting exactly when and where the metal sheet will yield under extreme pressure. The problem is a massive disconnect in scale. We apply huge forces to the bulk material from the outside, but the metal actually deforms by slipping along invisible, microscopic atomic planes deep inside. This chart maps the two spaces. The sample coordinate system is a macroscopic frame governed by external geometry, tracking outside forces along rolling, transverse, and normal directions. Conversely, the microscopic crystal coordinate system ignores external shape, dictated entirely by the internal atomic lattice. To accurately predict material failure, we have to mathematically bridge these two entirely different spatial realities. Consider a physical phenomenon, like a stress applied to a wing or the force of a structural load. That force factor is a tangible reality, fixed in absolute physical space. Here is the problem. We have a single, fixed physical vector, the green arrow. While that force doesn't move, its numerical components change entirely depending on your coordinate lens, whether viewing through the macroscopic sample frame in orange or the microscopic crystal frame in blue. Modern materials science relies entirely on finding a flawless mathematical translation tool to convert data between these specific reference frames. This diagram outlines how we define crystal orientation. It is not an absolute position. Instead, it is calculated mathematically as the rotational difference required to align the internal macroscopic crystal coordinates with the macroscopic sample coordinates. To execute this, we rely on passive rotation. Mechanics uses active rotation, physically turning an object, shown on the left. Crystallography uses passive rotation, on the right. The physical green vector never moves. Instead, the observer's perspective, the blue crystal axis, rotates around it. As the reference frame shifts, the numerical values describing the vector update in real time. The mathematical address changes, but the object itself remains firmly anchored. This cognitive shift aligns our mathematical viewpoint with the crystal's exact atomic planes, without altering the physical forces acting upon the material. The engine that drives this shifting perspective is a 3x3 grid called the rotation matrix or direction cosine matrix. This diagram breaks down how the matrix is built. Each element inside is a direction cosine, calculated by taking the dot product between a specific sample axis and a crystal axis. This operation mathematically captures the exact geometric angle between them. Let's put this into a practical engineering setup. We start with a known physical vector in the sample system, mapping out to coordinates 1, 1, 0. Our goal is to passively rotate our perspective by exactly 30 degrees. We plug that 30-degree angle into a standard two-dimensional rotation matrix. By calculating the sine and cosine, we generate the specific numerical values required to populate the matrix. To translate the vector, we multiply this final rotation matrix by our original sample vector. The output yields the precise numerical address of that force, now mapped relative to the crystal frame. The new coordinates point to 1.366 and 0.366. They look different than our starting values, but they describe the exact same physical reality, now translated into the language of the microscopic atomic lattice. We run a sanity check to verify this mathematical translation preserves the laws of physics. By calculating the vector's magnitude in both the sample frame and new crystal frame, we see the output remains exactly the square root of 2. Physical length is perfectly preserved. This preservation happens because both coordinate frames rely on mutually perpendicular axes. That exact geometry means our transformation matrix is orthogonal. This flowchart illustrates the powerful consequence of orthogonality. Reversing the translation from the microscopic frame back to the macroscopic frame is computationally trivial. You simply transpose the matrix. This elegant reversibility creates a robust two-way street, allowing engineers to reliably calculate how macroscopic constraints interact with microscopic behaviors. This direction cosine matrix operates as the literal logic hard-coded into modern materials science software. Without this exact orthogonal transformation framework, computers would be completely unable to interpret complex microtexture data like EBSD maps or model crystal plasticity. Mastering the crystallographic rotation matrix provides the exact mathematical link we need to calculate how microscopic atomic structures dictate the macroscopic strength and performance of the materials we build the world with.